Hello, Sully. Welcome to Luke's Lessons. Today we will be talking about organic chemistry. This is lesson 1. How the fuck do I do this? There we go. Structures and bonding, skeletal and Lewis structures. So, I'm sure you already know this, but we have our different kinds of structures. Right here, what I'm drawing is our Lewis structure. We have, our atoms represented by like letters with our bonds to other letters. Um, I picked a bad example for this. This will not have a skeletal structure, but acetone will. We have something like this. I'm pretty sure this is acetone, but if I'm not, it's still. This is, sorry, I don't know acetone, but I do know acetic acid. That would look something like this. With an O and an H out here. Now what this would look like is we start here, we go up, we go down, O, H, this is double bonded to an O. So each time we end off at either nothing or we switch directions, that is going to be a carbon. So there's a carbon right here, there's a carbon right here. Now, you might be wondering, oh well, there's a bunch of hydrogens attached to this carbon, why aren't we showing those? Because if we had like a big old molecule like this is nonane right here. We would have like what, 20 hydrogens we would have to draw out separately, and that would just be a whole mess, and we don't want to be doing that. For the models that you have, Sully, carbon would be black, hydrogens are white, oxygen is red, and nitrogen is dark blue. Each of these have a specific number of holes, so if you don't know, if I'm wrong about these, you can check the holes. Carbon will have 4 holes because we can see that it can make 4 bonds. Hydrogen will have 1 hole because it can make, or I don't know why hydrogen isn't on here. Oh well, it's over here in the middle, but it can make 1 bond. Oxygen will have 3 holes because if we look at our number of bonds, from here it goes down 3. Oh, sorry, it won't have 3, it will have 2 holes. My apologies. 2, 1, and then 0. So our oxygen will be able to make 2 bonds, and we can see that nitrogen will be able to make 3 bonds. And the single bonds are kind of like this. They're really rigid. They don't really flex all that much. And the double or triple bond ones are just slightly longer, and that's so you can really, like, there's going to be like a hole here and like a hole here, and so you can like bend them into shape almost. That makes sense. Then you can attach like 2 more things coming out the back there. Alkanes. So these are pretty integral to naming almost anything we will learn about in the future. So these you just kind of have to memorize. I know you probably don't like the way I memorize these, or it won't work for you maybe. But the way I learned these is I met Ethan properly in Bulgaria. I don't know. These first 4 are kind of just like names. Like they don't really follow a structure. The rest of these do. These are all just regular prefixes. So like pentane, you have a pentagon. Hexane, you have a hexagon. Heptane, you have a hectagon. Octane, you have an octagon, or like octopus. Nonane, nonagon, or I learned the as just, this is the only one with N, so it's 9, and then decane, like a dodecahedron. That would have whatever sides. Besides methane, the formula for how many hydrogens are in the molecule is the number of hydrogens is equal to 2 times the amount of carbons plus 2. We can look at ethane here and just prove it real quick. So our number of hydrogens is equal to 2 times the number of carbons, which is 2, plus 2. 4 plus 2 is equal to 6, and we can double check. That is how many hydrogens we have over here, and that would look like that. We have one, sorry, that wouldn't look like that. That would look like that. 1, 2, 3, 4, 5, 6 hydrogens on that thing. Now, we'll look at orbitals and hybridizations. So orbitals are just like where the electrons can be. This is all should be all review from Gen Chem 1. Our s orbitals are literally just circles. That's mostly, and our s orbitals are all going to be in the red. Helium really does belong over here, technically, but it's a double gas, so they put it over here. So all in red will have just a circle as their outermost shell, at least. P kind of looks like 2 dumbbells. And then D, oh, and P will also be everything that we have in yellow over here. And then D is going to be like a 4-leaf clover, but this one that I'm drawing right now is popping out and then back. So they're kind of like, I don't really know how to draw that, but it's like this one's going forward out at you. This one's going like perpendicular to the plane, like to the, yeah. And so D will be everything that's in these blue ones. There's also F down here, which is placed like kind of here. I don't know why. Wait, where is it? Oh, never mind. Sorry, never mind. They're placed here. There's like a little jump after the 5th row to the lanthanides and actinides. We don't need to know the shape of them, though. We don't really need to know the shape of these for organic chemistry either. We need to know the shape of the hybridizations, which for the most part will just be S and P. You only really get to D if you have 5 or more atoms bonded onto it, which is like just not going to happen really in organic chemistry for the time being. So our SP hybridizations are going to kind of be a mix between the two. You'll have one big head and then one little small one. And then if we have something like SP3, we'll have a bunch of those dumbbells coming out of this carbon. I'm sorry, drew that one weird. Bunch of dumbbells coming out, and that's why I can make 4 carbon bonds, is because it's SP3. Or that's what the bonds are made of when it's SP3. Sorry. And to figure out this number right here, we have the steric number, which is just the number of individual groups attached to an atom. So for example, we have, let's just say methane here, right? This is going to be SP3 because it attached to 1, 2, 3, 4 atoms. Yes, I'm right there, sorry. It's connected to 4 atoms. And on this next page, I have kind of a more in-depth one. So if we have 4 things attached, it's going to be SP3. 3 things attached, SP2. 2 things attached, SP. As I remember this, it's like I have 2 numbers total, or 2 letters total, S and P. I have 3 letters total, S, P, and P. And then just like math, you combine them into each other, and then you get P to the second. Not really like that means anything, but and then SP4, S, P, 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 combine it, SP3. And so the bond angles on these would be 180. If we have something like, not O, sorry. I'm just gonna make something up. Oh, perfect. If we have something like this, C, we have our H's. The bond angle here is 180. Yeah. Yeah. Yes, sir. No, I meant to put him downstairs. I'm recording chemistry lessons for Sully because he's struggling.
That's nice of you.
Probably gonna cut that out. Anyways, 180 would be our bond angle here because it's just a straight line. Here we have our sp2, which would be 120, and that's just 360 divided by 3, because this one is going, when you have only 3 things attached to something, no matter how they spin around each other, they will always want to be as far from each other as possible. And the only way you can do that is to be like planar, is to be like just completely flat. So if I go to skip ahead to my next slide, we can look at if we have 3 things attached, we'd be trigonal planar. 0 lone pairs, 3 electron groups, trigonal planar. And so the bond angle is just 360 divided by 3, which is equal to 120 degrees. And then sp3, the reason why it doesn't just follow it and become 360 divided by 4, which equals 90 degrees, is because when we have a sphere, it is better to be kind of a little offset. So this one's kind of coming out towards us. It's kind of on the front of this molecule, and this one's coming out the back, and then these two are in the plane. These ones are as shown. And so it's a little more from each of these bonds than 90 degrees. So it's 109.5. And then if we look at our molecular geometry, it's a lot of these we won't need to really worry about. Anything below here we don't need to worry about. These we definitely do need to worry about, especially the 4 here. The one we'll most often see is tetrahedral, which we can see here. The way I like to think of this is a tripod. Like, you got your tripod, and you recorded your TikTok videos as you do, right? And you're sitting here, you're dancing. Ooh, look at you. But yeah, that's kind of what this molecule looks like. Just imagine you got hydrogen, and then you got one leg coming out towards you, and one leg going out behind you. And this is the same thing that'll happen with your modeling kit. You'll have one right at the top. You can, if you line 2 of them up to be in the same plane as your view, you'll have one up top, one at the sides, one kind of out front here, and then one in the back. It'll kind of look like that. It's hard to really get it to look exactly like this, viewing it from a 3D model. This is the best that I could get for you. This is what your model is going to look like. But that is all of lesson 1. Thank you for watching.